Yes, good morning, everybody. It's my pleasure to heat you up a little bit more. I think Professor Kaplan was quite clear in some of his remarks, but my talk will change to a different field of science, that is engineering, that is product development in an industrial environment. And on the second hand, I will bring you to a very different type of scale. So we were starting in the nanoscale, and I will show you about the importance of ceramics in real huge industrial systems. Stuttgart University is nearly 180 years old, and it is one of the top 5 German technical universities where we have product development from the basic idea and concept to the complete realization to the complete pilot plant. And with this background, we look to the complete process chain when creating a new product. This is a quite different part of the chain where we look to the challenge, not in love with the materials, but with a clear focus on the performance of the technical system. So materials and process engineering is just a part of the complete engineering concept. So if we look to the strategic materials development where it is connected with new technical systems, we may separate what are the main functionalities, but we are talking about a term called simultaneous engineering. And this means material science and process and manufacturing engineering are not going different tracks for years. That is the situation we had in Europe for more than 2 decades. And at the very end, most of us had to learn from each other that we lost a lot of time, money, budget, effort, men and women years. We should do it better. And this means since the early beginning, we should include in our strategic approach which is the most feasible manufacturing technology to get access to this new generation of products. And that means materials and product engineering should not be any more contradictory. And I will show you some examples of the past, what really happened, and what will be the challenge for the next generation, and this is your generation. Modern materials today include advanced electrophysical properties, thermophysical properties. We have a lot of approaches in the field of biomedical devices, but last not least, advanced mechanical engineering is still the backbone of our economies. And as a German citizen, I know quite well what I'm talking about. Therefore, in these few minutes this morning, I will have a close link to advanced ceramics in advanced mechanical engineering applications. We had a short talk during the coffee break with Professor Moya yesterday, and the subject was how are new things, new material concepts getting to be a product and coming to the market. And with this draft, I will try to show you it's much more complex. Material science is just one issue. We have plotted the engineering relevant in red. You see, it is a quite complex scheme how to create a product, but also how to bring it to the market. And for sure, what we need is the human being, where we have the ideas, where we have the creativity, where we have the basic motivation. But we have also to think about what is going on in the market. That means quite different disciplines that are not originally taught and learned by the material scientists. And I want just to use these few minutes to make you a little bit sensitive, more sensitive and aware what will be the challenge whenever you will come to a position in an industrial environment where you have to take responsibilities and not just producing papers and data and Professor Kaplan, one of my colleagues in industrial management, he was talking quite harder than you did. He said, some of the papers we have here on the desk, their only value is their caloric value. That means when you burn them. So I shall never forget when my company bought a license, or was on the way to buy a license for advanced zirconia materials. That was in the early 80s, the wonder material of the world. There was a quite famous professor, and he was quite serious, and everything was working perfect until we started how to reproduce these material properties. But what happened? What happened? It was not in the ppm range. It was not in the per millar range. He did use about 1% of the mass of his attrition mill and modified his recipe. And this is just one example that the transition from laboratory results in a serious engineering that is required for an industrial application is a very different matter and a different challenge. And what we are teaching our students is not just the processing and the material science and engineering, but they have also to work in new manufacturing, new fabrication techniques. And this includes process automation, advanced process control systems to achieve reproducibility, and last not least, to think and to work how to fulfill our cost targets. Because if you really want to deal with a product that has a potential in the market, there must be a fair ratio between the cost and performance, or the technical performance and the economic facts. And last not least, we have to think about social and legal restrictions. I was chairing Germany's largest joint project in visco reinforced ceramics, and I shall never forget when a top manager of a big industrial group invited his chief medical doctor. And 5 minutes after we started the big meeting, the project was ended because the hard facts were on the desk about the health risk in handling these whiskers. And you all may be aware that we have to face similar problems if we are working with nanomaterials. We need special safety standards in handling, in compounding, and again for all the process chain. Why are people choosing ceramics? You all know about the advantages of ceramics. We all use these facts in our introductory remarks wherever we gave a plenary talk. But on the other side, we have not only to face the problems with their brittleness. I will not take so much time with this subject. And we learned in a very impressive way about the importance of local stresses and stress distributions in the first paper this morning. But there is different challenge, because in a product you have a geometry, you have a shape, you have tolerances of the material. It is not enough just to think about the material's properties, but about the component. That makes a big, important difference. And therefore we have to work hard to develop the most appropriate manufacturing techniques, or the set of techniques we apply. And this for sure includes the compounding, the forming and shaping, and all the thermal process engineering. And last not least, what remains is the effort for the machining in the final state. That means in the sintered state, the handling of hard and super hard materials. Today we have much more experience with that, and this is one of the reasons why many decision makers in the important industries get more and more skeptical towards ceramics. The era of emphasis, of great emphasis of ceramics is over. Daimler-Benz closed their ceramic research facilities 2 years ago, completely, switch off. Höchst, Bayer, the big chemical, switch off. And what is the reason for that? We all together have to share the responsibility for this situation, and that is the mismatch between the requirements of material science and engineering on one side and industrial product development and process engineering on the other side. With all these drawbacks and risks in the application of structural ceramics, we have to think which can be the most appropriate strategies. First, to improve the mechanical, but also further specific properties of ceramics. And again, I'm not talking about materials, I'm talking about components, whatever may be their size or their design. And for sure, there is the classic approach, the microstructural optimization, and this is not old stuff. We should apply some of the philosophy of Kaizen, the continuous improvement process. Sometimes we should be modest and also accept to achieve improvements by small steps. But many, many small steps give us serious progress. Not just big words, big challenges, and no achievement. We have learned this morning about the incorporation of additional solid phases. I said it in a very abstract way here, because we can talk about ductile phases like metals we have seen it this morning, or we can use the zirconia toughening effects by phase transitions, stress-induced phase transitions. And last not least, we may integrate additional solid phases with a special aspect ratio, not only particulate materials, not only whiskers, but also short fibers, endless fibers, and even complex textile structures. And this, for sure, will lead us to fiber composite materials. And there are the layer composites. That is when we completely separate the structural properties and the functional properties of the surface of a component. Professor Kaplan was giving the term of laminates, but we can also talk about coatings. Coatings where we apply the lightweight engineering potential of alumina, magnesia, and other alloys and give them a ceramic surface. An important strategic feature also in our integrated project NanoCare. And again, last not least, how to include the innovations in the manufacturing technologies to achieve reproducible high-quality standards. As material scientists, you are well aware with these various strategies, just to keep in mind how the microstructures of these materials may look. The standard but modern fine-grained alumina as a structural material. Then we can have the structural refinement on the conventional track using submicron aluminas. We can use a transformation toughening effect, and that makes it easy for me in the second presentation, as you are still sensitive against these oxide, non-oxide, micro nanocomposite materials. And the same may happen in the combination of different non-oxide ceramics. So what remains is to think about the processing route. And it is quite easy to estimate that for an endless fiber reinforced ceramic structure, we need completely different forming and shaping, and also including compounding techniques, as for a traditional powder ceramic or powder metallurgical part. So if we stay a little bit away from our own background in material science, and we try to take the coat of the customer, that is the person who should pay for our product, then we should summarize what may be the most important customer demands to ceramic components. And again, not to ceramic materials, to ceramic components. And for sure, there is the high mechanical strength, there is the good abrasive and chemical resistance, there is the high temperature strength, and hopefully the good creep resistance. And a little bit later we see we leave these typical material features, and there is such a word like dimensional tolerances, surface qualities. How to measure that? And you see, you need a different education, you need different tools, and you need a different understanding. And the second is to understand which are the key parameters in all these process steps of the process chain. And at the very end, we have to calculate the economic effect of all these means and methods we employ. And last but not least, we have to think about the time scale, not the time scale of crack propagation, that is another interesting matter, but the time scale, how fast the well-defined product will come to the hands of the customer. And this is not the end of the list. So if we go to the other side, to a professional ceramic manufacturer, yes, he knows very well that he has to organize a cost-effective production to serve to his shareholders, but he is also in charge to achieve the customer satisfaction. The customer orientation is a key issue to be successful in international business affairs. And for sure, this includes a deep understanding of the specifications of my product and its quality characteristics. But you may be aware it is a little bit more. It is not just the usual material properties. We are also thinking about data from a professional quality management, statistical process control data, an example. But the most important thing is, if we know the lot size, the design, the geometry, the set of tolerances, to select the most appropriate manufacturing process. Because in most cases, there are variants, you have alternatives, but you have to meet the best one. And I will try to show you in some examples, in some little case studies, how this may work. Okay, we have again the consideration, the professional consideration of the drawing, what we call the drawing in mechanical engineering, really to fulfill the requirements for a sophisticated machine system. The dimensional tolerances, the surface quality, the quality requirements in general, including the material properties, but now a piece of another world. Scrap rates. Never heard the word of scrap in these days. Yes, for sure. But this happens for a real product. And we have to know and to learn about it. And it is not a shame. It can be great to have a scrap rate of 80%, but the 20% that remains are a beautiful product with an excellent price on the market. Lot sizes. Lot sizes may be a stupid matter for a material scientist, for a manufacturing engineer. It is the decision-making point. It is a big difference if you produce just some individual parts or a few dozens, or if you have to produce a few 100,000 a year. Completely different technologies, completely different tools, processes, machines. And this also refers to questions like operation lifetime of our investment goods, of equipment, of the tools, and further technical components employed. And last not least, we have to monitor again every cost relevant factor in this process chain. So if we summarize this, we have two fellows, and that is the main motivation for this presentation this morning, to bring these two guys together. And you see, here we have our material scientist, and he is educated and he is motivated, like in the classic Greece, where we have the Olympic motto, not in Greek but in Latin, Altius, Citius, Fortius. Performance, performance-driven. And you see they are dreaming of a tensile strength of 2,000 megapascals. They are dreaming of Weibel coefficients more than 30. But look to this guy here. His eyes are different. He has the dollar sign in his eyes. And here it starts. Sorry, we have no more French francs, je regrette. There are no more lira. I have not plotted the Deutschmark here because so we got tears in our eyes. But more important is that there is such a term like GIT. It's not a parameter. It's a strategy. Just in time, just in sequence. But an important parameter, CPK, the key parameter in statistical process control. And if your CPK value of the total process chain does not achieve the 1.4 as something like a dimensionless number, you will never be accepted as a supplier. You can forget about all your understanding of your research. There is no chance. That means such a simple, stupid figure gives you the benchmark how to organize your process chain, how to organize your factory, and how to create a high-quality, reliable product. And you see, he is summarizing in a quite different way. Not performance-driven, he is cost-driven. Cheaper, easier, earlier. You may say faster. And that is what I want to motivate you to think about if you are planning your career in the near future. Now to the real facts in our business, the selection of the process route. We have different sets of requirements, and for sure there are the material properties, and I don't want to repeat so much the engineering criteria, but this set of requirements is in any case mandatory. Mandatory. And let me just look to, in a very simple way, to the principal tracks we can go in manufacturing. We can use one of the famous pressing techniques, we can use a casting technique, or we can use plastic forming. Plastic forming, immensely important in an industrial environment, and I am always disappointed how poor is the research effort in this field. The question is to make the decision, is it appropriate, yes or no, and is it feasible? So we end in a quite complex selection process, and hopefully we find it. Hopefully we have a solution. In some cases we may stand there with empty hands, and we may summarize we have to develop it really starting with a blank white leaf of paper. Now a few words to the processing technologies. As I was asked to give some introduction to this matter, and you see how we organize it also in our general lectures: casting, plastic forming, and pressing. And for those one who are not so familiar with that, you can also summarize it with an increasing content of solvent, may it be water or an organic solvent. Or you can also summarize it from the viewpoint of fluid dynamics and think about the rheological behavior of these various compounds. In any case, we have a nice portfolio. And we have a nice portfolio that may be appropriate also for the processing of nanopowders. Dr. Kern and the further colleagues in this session will give you much more precise details to that. And we have some special techniques like screen printing, tape casting, special injecting devices. But very interesting and we have a strong focus actually on this business: extrusion, injection molding, and also such techniques that are a little bit a hybrid to casting, like the hot casting as a special feature of the injection molding. And last not least, we have the pressing techniques. I did not include the SPS technique because I think this is a special subject. And last not least, there are the rapid prototyping process roads that play an important role in the initial phase of product development, but I'm quite skeptical that this will really be a long-term alternative. So the casting road, everybody in the lab started with a nice form of plaster and learned how to make hollow products or bulk products. And it is a little bit more sophisticated to use a computer-controlled pressure slip casting machine. But for sure, if we have to produce a few thousand pieces per shift, there is no alternative. Otherwise, we should use all the center of Greater Madrid as a stock for the plaster forms, and this will not work for sure. From the viewpoint of the product developer, it is important which are the typical wall thicknesses I can achieve and how fast works the process. Sorry, there was no time to translate this in English, but you can just see the pressureless casting and the high pressure casting. It is half an order of magnitude or even a full order of magnitude in the speed of forming the material. Just to get a first feeling. But for sure, we have to make a decision that is well balanced. What about the investment cost of such a track in comparison to the traditional method? And you see, there are general aims. We want to have reproducible and uniform deposition speeds because the complexity of the shape is an important factor. A simple plate, a simple cylinder, nobody will pay you a nice or effective price for. The more complex you can create the shape of your part, the more is the success you can have in business. Now to the different scale, because the stabilization of our individual particles play an important role, not only in basic science, not only in the laboratory, but quite important in an industrial batch size. And that can be a batch size of a few tons in some cases. And the homogeneity in a cubic meter batch is a different challenge in comparison with a 10 cubic centimeter glass batch. Paul will give you more details to that. I will shorten that a little bit. But just one early experience when we started with the casting of far submicron nanopowders by traditional pressureless casting. And in about 25 years, we developed a lot of very well studied recipes how to achieve a very high content of solid. A stable suspension, but also a very high content of solid. We learned so much about sintering yesterday, but without a high green density and a perfect homogeneity in green state, it is a hard job to compensate all the defects by the thermal processing. The better you are in this early state, the easier is it to achieve the final goal. And you see, it was not so difficult if we came down from the traditional particle size in the submicron size, but as soon as the powders are smaller than 100 or 80 nanometers, there is a distinct drop in the achievable solid content. And that has a distinct influence and important consequences for all the manufacturing, because the lower solid contents, they lead to a less favorable process characteristics, and the most important critical factor is the shrinkage during the drying operation, and for sure the high shrinkage rate to achieve full density of the final component. That means the smaller the particle, the higher the volume fraction of solvent is necessary to stabilize the dispersion. And this is a clear contradictory approach for a manufacturing engineer. Pressing techniques. Axial pressing, if you talk to Siemens, to Robert Bosch, the big players in the market, more than 90% of their ceramic components are made by axial pressing and cold isostatic pressing. It's easy to understand, but it's not so well known, because so many of us in the lab are in love with casting operations. But there are some risks with the pressing. With the axial pressing, we have inhomogeneities in the density, even if it is a simple geometry. And if we apply the cold isostatic pressing, it may happen that we have to face an investment far more than 10 million euros if we really do it in the large scale. Nevertheless, cold isostatic pressing with subsequent advanced machining, we call it machining in green state or green machining, for many applications in mechanical engineering until now is one of the most performing manufacturing routes. Also related to the required material properties. But you see, there are different challenges. The material properties and the component properties may depend on such stupid things. If you change in a multi-stage machining operation, just positioning errors can kill your product. If you have ultra-hard materials, you would like to work with an additional wall thickness or an additional dimension of just a few microns if possible. But this will not work if the tolerances you have in your cutting or drilling or milling machine, these tolerances are not appropriate to the product you want to make on these machines. And last but not least, we have to think about such stupid things like edge chipping. That is the entering and the leave of the cutting tool in the material and the mechanical response of your ceramic in green state. Wow. And this is one of the reasons why, as a modern ceramist in industry, has to develop or has to bring with his original education a deep understanding about polymers, because the chemistry and the technology of advanced binders is the key issue. And I will just show you this in one case. 3-point bending test, very primitive in this type of testing. But let's look to the figures, what we can achieve as the so-called strength of CIP components in green state. And the limit for processing by a modern turning operation is in the range of just 20 megapascals, so that's not much. And you see, even for submicron ceramics, we can achieve that, but it is not only a question of the powder design, of the grain size distributions, or of the grain design of our component. It strongly depends on the additives. With respect to my former company, I cannot disclose their special know-how, but you see, in one single case, that was synthetic molite, we were not able to develop a binder and an additive recipe that these materials could really be machined to the standards of this company. And the reason is the surface chemistry, and this again should show us that the manufacturing engineer strongly depends on the knowledge and on the know-how of the material scientist. And if we want to have a product together, this is also true vice versa. So the portfolio of these products is a quite broad one. There are a lot of small and complex parts, there are larger parts, and there may be very huge parts. And I will just use this little case study. That was the first generation of the so-called European weather satellite, developed in the early 80s in Germany, and the requirements were clear. There is this large ring structure with a total diameter of about 80 centimeters. And with this diameter, you may guess what is the dimensional tolerances to have a very precise ring structure with such a thin, relatively thin wall thickness. What you cannot see from the chairs behind is that this structure contains 1,200 micro holes, micro bores. How to produce such a part? How to produce such a part? There was only one supplier who could fulfill the requirements, and this was made by cold isostatic pressing of a full solid block. More than 95% of the volume were cutted and drilled away, more than 95%, and the scrap rate is always a secret. The most important thing was to bring out 6 correct parts that could fulfill the requirements and specifications. But you can see, to produce this part in green state, you need a cold isostatic press with a diameter of about 1.5 meters. And this again should give you an idea how important it is to think about what is the machining, what is the investment good behind this ceramic chain. And here you have also the key issues. What were the dimensional tolerances for the diameter and for the wall thickness? And for sure, this part had to stand the full acceleration and the vibrational stability during the rocket launch. Not just to talk about the thermoshock, day and night in space, sunny side and shadow side. What does it mean, vibration? Professor Kaplan made a remark about 3-point or 4-point testing. This is a static test. This is a single event. To use a ceramic with a high cycle fatigue, 100,000 load cycles. That is the real challenge. And this is one of the reasons many people never speak about why ceramics are not so easily accepted by the mechanical engineers for a dynamic machine system. Injection molding. With respect to the time, I will reduce that. Frank will tell you that a little bit later. So before I come to an end, another important case study. That was my early beginning when I finished my career as an assistant professor at Karlsruhe University. My company was in charge to develop high precision ceramic tubes for an application in this well-beloved country in southern Spain. And this is not photovoltaics, this is the focus of solar power, thermal power. So this is the concept of the famous Plataforma Solar in Almeria. And the focus of all this huge field of mirrors is in the center of this tower here. And the challenge was to develop a heat exchanger that can work with gas temperatures on the surface up to 2000 degrees C, high temperature and oxidation resistance. Quite nice with these extreme. That is really extreme applications, extreme. But I will tell you in a minute The problem was not the material primarily. The problem was a heat exchanger with such an extreme load needs absolutely precise, straight, and perfectly round tubes. And in this set, there were about 1,000 pieces. 1,000 pieces. And I make it short, only silicon carbide, at least at this time, was the appropriate material to overcome and to develop the technical solution. Here you have it a little bit in a higher magnification, how it looks in the center point of this heliostat, and the thermal power was about 60 kilowatts, not on the primary side, but on the output side. But for sure, this sun kiln did deliver steam. Steam. Yes, which are the materials? Everybody was in love with hot-pressed or isostatically hot-pressed material. Can you tell me who has a press for a tube of 2 meters length? No. The solution was a lousy material, a relatively lousy material if you just focus on the material's properties. Silicon infiltrated silicon carbide. One handicap, we must stay in a safe distance to the melting point of the silicon. That was the ultra fine-grained material developed in Harwell by our British colleagues for their nuclear power plants. At the time, it was the finest silicon carbide material that was reaction bonded or siliconized. And the advantage in mechanical strength was quite impressive. The question was, can one or two or more of these materials be processed in the shape of a high precision tube? Of a high precision tube. And for sure, to produce a tube, you select the extrusion technology. That means you have to develop a performing extrusion feedstock, a compound, to adjust the plasticity and to adjust the viscosity. But what counts at the very end is the form and dimensional stability and the stiffness of the extruded part. And in a second, I will show you the hard facts about the dimensional tolerances of this material. And you all know silicon carbide has absolutely no plasticity that can be exploited for forming and shaping. And we can hardly use a distinct amount of inorganic additives. That means all the plasticity, all the rheological behavior, and that means also the strength and the handling safety in green state must be performed by a set of optimized organic additives, binders, plasticizers, and further auxiliary products like dispersing and wetting agents. The most important are the temporary binder systems. Temporary with respect to the thermal treatment, to the sintering, or to the reaction bonding. Everybody knows extrusion can be done with a piston machine or with a screw machine. A screw machine leaves you always with a texture in the material. And this texture really may be the memory effect of the screw and the flow behavior during the extrusion operation. So after we had worked for about a year with the most sophisticated, most expensive screw extruders, one of the most experienced masters in the factory said, "Oh boss, forget about it. Let's try to use a piston extruder." A piston extruder. Okay, not so much details about it, just to show you the end of this product development. There was a parameter called TIR, total indicator reading. This summarizes the bending, the curvature, the ovality by a turning measurement, high precision measurement, tactile measurement on the tube. And the original specification was to achieve 1 millimeter length per 1 meter length of the tube. That's where we started, and even in the early phase there was no competitor. And that's where we ended. And these are some data of the, this is a binary grain size distribution, where the coarse fraction is the FEPA grain size 360 and alternatively the 430. And what I will show you here is we started with the idea to realize the potential of the refill material, 500 megapascals. And refill material is 0, is here. And we ended with a material with a coarse grain fraction of about 70%. If somebody would have told that to us 1 or 2 years before, maybe somebody would have fired him. But that was the solution, and this is not only true for the reference project of the solar power plant, it is also true for a complete product family of ceramic heat exchangers. So this example should just serve, it should not be representative, just to give you a certain sensibility that the problem of precision of the component is a very decision-making point in all these advanced materials. And now, before I come to the end, just a very few words to the nanocomposites. Because our primary aim and scope, and this is not changed until now, is we want to exploit these general forming and shaping methods as far as possible to create structural ceramic materials, ceramic components, by the application of a new generation of powders and further developed or even novel forming and shaping processes, because we think that there is an interesting window for materials with superior properties. And I don't want to make further references to our estimated colleague Nihara, but with respect to time, allow me to summarize that the challenges in manufacturing of ceramics are a little bit different to the original aims and scopes in the pure materials development. And this is a traditional conflict between engineers and material scientists since half a generation at least. But for the near future, we should learn from this disaster of the past. We should bring together the people, and since an early state, they should have a common commitment that this new generation of forming and shaping technologies, all the important steps in the process chain, should be fast, should deliver a product with very narrow tolerances. That means a clear net shape strategy. I think Frank will go in much more detail in this field. And we have also to work in an energy and material efficient way. Energy and material efficient way. The challenge to save energy is one of the first strategic approaches in the modern industries. And the factory of the future will have a completely different energy balance, whatever we have seen until now. And last not least, we have commonly to carry the responsibility for the occupational health and safety requirements in the handling of nanopowders. Thank you for your attention, and we enjoy the further discussion.